This is our introduction video to cross sections, which is where we're finding volumes using infinite sums or the integral. So it's really a conceptual video. I'm going to start just with a generic region here. Say I have this region that looks like this, and it gets established that I want to find this region here, which we're just going to keep it simple. We're going to say that it's going to be the top curve minus the bottom curve, and we're going to call that our base value. So we're just looking for this region right here, and we're going to call that our base value. So we'll say this is from A, and we'll call this thing right here B. And so I'm interested in that region. Now it's not being revolved. Notice that I didn't say solids of revolution. I'm talking about physically creating, this is the base of my object, and I'm going to have this protrude. It's going to project from the paper out. It's going to become a three-dimensional object. And so for something like this, you would establish that you have a base, which in this case would be the top function minus the bottom. So generically we'll call this f of x, we'll call this g of x, and so we have a base that is defined as f of x minus g of x, whatever that may be. That's my base. Now the part that I want to establish is what's going to happen with this, the types of problems that you can see. Most commonly they'll say, let's have this come out as an equilateral triangle. So you have all these equilateral triangles that protrude out and they end up connecting. So it gives you this three-dimensional object that sets its base right on that paper. I could set that right down there. It's almost like doing a 3D printer. Now once I have this base, I have to figure out any one of these triangles what I'm working with, because if you recall, a volume, when we were doing solids of revolution, for a disk we'd say pi r squared, that's a circle, times dx, which becomes a cylinder. So it's pi r squared dx. So it's the area times a dx or a dy, whatever the case may be. We did the same with the shell. We come up with 3 dimensions. So nothing would change here. I'm going to do the integral from A to B, but what I have to have is an area function with respect to x in this case, because what will happen is I'm going to cut this perpendicular to the x-axis. So I've got a billion of these or more, that's my dx, but I have to come up with what the area would be for an equilateral triangle. So that's what we want to start with. I'm going to go to a separate sheet of paper here so I have a little bit of room. We'll call this A. Equilateral triangle. Equilateral triangle. With an equilateral triangle, I'm just going to look at a cross section here. I know that this distance on the bottom is the f of x minus g of x, but for the sake of simplicity, I'm just going to call it base. I'm going to say this value here is my base. Because it's an equilateral triangle, if I were to drop a perpendicular, this would create a 30, 60, 90 right triangle. And if you recall, this would be half my base. I'm just going to use B for base. We've got a ratio for 30, 60, 90 right triangle. If you take twice the short leg, that becomes your hypotenuse, which makes sense because this base should be the same as this if it's an equilateral triangle. And the height becomes whatever the base is times rad 3. So this would be radical 3 over 2. That's the same as 1/2 times rad 3 times the base. Now as I put this together, my area would be 1/2 the base of a triangle times the height. Now when I say base, I'm not talking about this base, but actually in a sense I am. So I can say this, 1/2, my base is this base, so I can say whatever my base was. And the height, well, we just figured that the height of the triangle is going to be rad 3 over 2. So I can say rad 3 over 2 times the base, because that's what this b was. To simplify this, take the two fractions. 1/2 times rad 3 over 2 becomes radical 3 over 4. Base times base is base squared. Which means if you're going to do an equilateral triangle, your integration would simply be the volume equals the integral from A to B, radical 3 over 4, whatever that base is. Now from problem to problem that would change, but it's going to be calculated as if it's slicing the x-axis, top minus bottom. So, you know, your picture could change, but the concept doesn't. This formula never changes. And so it would be f of x minus g of x for slicing perpendicular to the x-axis. And so you could say base squared, whatever that part would be, you'd have to figure that part out for each problem. Now see, that's my area. And what I was saying is you need to have an area function times the infinite slices. So I'm going to slice this infinitely many times. I'll have an infinite number of these triangles creating this. So I have to add those up. And the depth of each one of those is just going to be dx. And so that's your setup for an equilateral triangle. Now you're going to have a bunch of different shapes. So we're going to do a couple of these here. We'll go to B. Maybe they want a 45, 45, 90, where the hypotenuse is your base. So again, just a quick drawing here. Let's do something different this time. Let's say this was the region that I had, and I want to go like this. That's my hypotenuse, and it comes out like that. And so I'd have an infinite number of these. The concept never changes. You'd say the volume is equal to the integral from A to B for an area function dx. Now when you add all those areas up, it becomes a volume. That's what we're saying. So when we look at this picture, here's my attempt at a 45, 45, 90. If I drop a perpendicular, I know that this is my base. This base is defined as that top minus bottom function right here. So I've got my base, which will be f of x minus g of x for all intents and purposes. And so I've got this base. If this is a 45, 45, 90 and I drop this here, that means that this would be a 45, 45, 90. And so I'll just draw this component here. If the base is the whole length, this would be half the base. And because this would be a 45, 45, 90 as well, you see this is 90 or 45 here, this 90, that has to be another 45. The legs for a 45, 45, 90 have to be the same, so this is also 1/2 the base. And so I put this together and I can say my volume would equal the integral from A to B. The area of this would be 1/2 base times 1/2 base, which I think we can do in our head. Half times half is a fourth. Base squared dx. And that would set up our volume, our integral for our volume, where you're replacing the base with whatever these functions are, the top function minus the bottom. And this goes both directions. So if I had a slicing that was going perpendicular to the y-axis, I'd have to do the rightmost function minus the leftmost function. We'll get into that when we do specific examples. Let me keep rolling here. Let's do a letter C. And this one might seem a little bit weird because we've done our solids of revolution, but I want to have this being semicircles. So the difference on this is that when you are doing the slicing technique, you're able to establish a region that your volume would actually sit right on. So maybe it looks like this. This is my region. I guarantee you that if I cut this out, I could put my volume right there, whatever that item is, and then it would just come out from this paper. It'd have this flat edge. And this has to be semicircles. I don't know why I'm drawing it this way. This is going to be horrible. But you can start to see what I'm trying to do. This would be a three-dimensional object that is protruding from the paper. And so I would say my volume equals the integral. This would be my A, this would be my B, from A to B. A of x times dx. I need the area. So I've got a base. Would be whatever f of x is, f of x minus g of x. Top function minus bottom function. And as I look at a cross section of this distance is my base. So I've got a base here. In order to find this area, well, I'm going to need a radius, and this length would be half of that base. The area for a semicircle would be 1/2 pi r squared, where r is this half base. So I'm simply going to plug that in for r. And I square it. But if I square it, half squared is 1/4. So I get 1/2 pi times 1/4 base squared. A half times a fourth would be 1/8 pi, whatever my base is, squared. That's my area. And so then I can come up here, generically, I'd have the volume is from A to B, 1/8 pi, and then I've got whatever my base is, which again, that changes from problem to problem, squared dx. And so that's how you would do your semicircles. Now, they'll have other shapes. Those are the three major ones. They can do things like rectangles of height 5. And so I'll do a real simple one like that. We've got a rectangle of height 5. Those are actually the easiest ones. I don't even need to draw a picture on that. You would just go, the volume equals the integral from A to B, A of x dx. So when we do this, your A of x is simply going to be your base times 5. So it'd be 5, because that's the area of a rectangle. 5 is the height. The length of that would be whatever your base was, your f of x minus g of x, dx. Height of 7, you change it to a 7. Height of 12, you change it to a 12. And you could even get complicated. You could say that you have rectangles. You could do weird things, or not rectangles, trapezoids. You could do trapezoids. So as a last example for this conceptual video, let's talk about that. Let's be weird. Let's do a trapezoid where the top base is twice, 2 times, the contained base, the bottom base, and let's do a height that is 1/3 of the bottom base. Now, obviously, this would change from problem to problem to problem. All you have to do is know the generic formula for a trapezoid and plug those things in respectively. So I do want to do a little graph here. Say I had something that was looking like this. Now, visualizing this may become a little bit of a challenge, but once I establish this base, I know that it's going to come up just a little bit, but the top base has to be twice that bottom base. So this thing's actually going to protrude out. It's going to go something like this and then come back in. And then I have one here, comes up a little bit, but then this has to protrude out. So as I'm drawing this, if you can visualize it, it's almost like the skeleton for a canoe boat. These would be like your ribs. And then of course this would all attach. Boom. And it would have this flat bottom because it would sit right on that piece of paper. So it's 3-dimensional. Now the work for it, I would say the volume equals the integral from a to b. Now I've got to establish what this is. This would be an a of x dx. But that a of x may be a little bit of a challenge, because this is what I'm looking at. Here's the cross section. I have my base. I know that the height is going to be 1/3 of this base. And this exterior base, the protruding base, is twice the bottom base, so this would be 2 times the base. Now you have to put that together and hopefully you remember how to find the area of a trapezoid. The area of a trapezoid would be 1/2 base 1 plus base 2 times height. I know I'm using a lot of the same letters, it may become a little bit confusing. Just take your time and think through it. So my bottom base in this case would just be a b. I'm just going to call that a b. So I'm going to go 1/2 b. The top base is 2b, so say plus 2b. And the height, well, the height is 1/3 of the base, so I go 1/3 base. Now when I put this particular example together, I can do my multiplication. 1/2, well, actually it'd be simpler if I just did this. B plus 2b is 3b. 3b times 1/3 would just be b. So if I look at this part, 1/3 of 3b is just b. So I got 1/2. And then I got this base here, base. So it'd be 1/2 bb, or 1/2 base squared. And so I could say that my volume would be the integral from a to b of 1/2. Now, when I write this, I write the word base because base would be whatever that top function minus the bottom function was. So I go base squared dx. And so there's a visual or conceptual look at how you can do these volumes by slicing. I'll come back, I'll do a couple examples with specific problems. We'll do the perpendicular to the x-axis, perpendicular to y-axis, so you can see how this goes with specific problems.